There is a story that seems, at first, like a coincidence, so common it becomes invisible. Nearly everything turns. Planets turn, and their skies will overhead. Moons turn, though many keep one face locked toward their parent worlds in a slow, enduring pact. Stars turn, sometimes with such speed that their equators lift and their poles flatten, their surfaces carrying magnetic storms around and around. Whole galaxies turn, vast pinwheels of stars and dust, their arms traced by blue light and the cold glow of molecular clouds. Even the most diffuse structures, the sprawling gatherings of galaxies, carry motions that echo the ancient shove and pull of their formation. On Earth, hurricanes turn and water-draining turns, and the very air seems to prefer curved paths whenever it is given scale and time. Beneath that, at the scale of molecules, electrons and atoms occupy states that carry angular momentum, and nuclei have spin, and the quantum world seems haunted by rotations that are not rotations in the ordinary sense, but are just as real, just as conserved, just as woven into what matter can be. And so the topic is not merely that the universe spins. The topic is why turning appears so persistently, why rotation is not an exception but a default, why a straight path so often becomes a curve, why a cloud so often becomes a disk, why a disk so often becomes a sphere that turns, why a turning sphere so often acquires companions that also turn. And in that, why, there is a deeper demand. Not a demand for a poetic answer, but for an answer that survives contact with measurement, with mathematics, with the austere insistence of physical law. The universe does not turn because it prefers beauty, though the result is often beautiful. It turns because certain quantities do not vanish when chaos unfolds, because certain symmetries of nature leave behind invariance, because motion that could have canceled instead becomes trapped in shape, and because gravity, patient, indifferent, relentless, collects wandering matter into forms where spin is not easily erased. Rotation is what happens when motion is constrained. Rotation is what happens when there is a center and there is momentum that cannot be simply destroyed. Rotation is what happens when there are torques, and when there are no torques, when collisions redistribute motion but do not eliminate the total. Rotation is what happens when a system has energy it can shed, but angular momentum it must keep, and so it changes shape to accommodate that stubbornness. In the universe, energy can leave in many ways: heat, light, radiation, shock waves, neutrinos, gravitational waves. But angular momentum is conserved with an almost ruthless fidelity unless something external can carry it away. And in most cosmic settings, external is a complicated word because the universe is not full of fixed anchors. It is full of things all moving together, exchanging momentum internally, rarely offering a convenient place for spin to go. To understand why everything spins, the mind must begin with something almost embarrassingly simple: motion. Not motion in a philosophical sense, but motion as a measurable change of position over time. In everyday life, motion feels easy to start and easy to stop. A hand pushes a cup, the cup slides, friction steals its movement and turns it into warmth. A thrown ball rises, falls, and comes to rest. This familiarity hides a deeper rule. In the absence of forces, motion persists. If there is no friction, no air resistance, no contact, no gravity, a body in motion continues in a straight line at constant speed. That is inertia, a word that means more than stubbornness. It is the statement that velocity is not something that needs to be continuously supported. It is something that only changes when acted upon. Rotation is a cousin of this. Just as linear velocity persists without force, angular velocity persists without torque. A torque is to rotation what a force is to translation, the influence that changes rotational motion. When a skater spins with arms extended and then draws them inward, the spin rate increases. This is not because a new torque has been applied from outside, but because the distribution of mass relative to the rotation axis has changed, and the angular momentum, an intrinsic measure of rotational motion, must remain constant. Angular momentum is the product, in the simplest cases, of moment of inertia and angular velocity. Moment of inertia depends on how mass is arranged relative to the axis. Pull mass closer to the axis, moment of inertia decreases. If angular momentum is conserved, angular velocity must increase. This is not a trick, it is a law. In the real world, the skater is not perfectly isolated. Air resistance and internal friction exist. Yet the effect is dramatic because these dissipative influences are small compared to the conservation constraint over the timescale of the movement. The skater demonstrates in a human body what stars and planets demonstrate on cosmic scales. When matter collapses inward, spin accelerates. When a cloud contracts, when a core shrinks, when gravity pulls material closer to a center, any tiny initial rotation becomes larger. Not because gravity adds spin in some mystical way, but because it changes the lever arm of existing motion. The universe begins not as a clean slate, but as a field of tiny irregularities. In the standard cosmological picture, the early universe is hot, dense, and expanding. It is also not perfectly uniform. There are minute differences in density, tiny variations that later become the seeds of structure. Gravity amplifies these differences. A region slightly denser than its surroundings attracts more matter. As matter falls inward, it rarely falls perfectly straight. The infalling matter carries random motions inherited from the thermal state of the early cosmos and from subsequent interactions. Those motions can be decomposed into components, radial components toward the center and tangential components sideways. The radial components can be redirected by collisions, shocks, and gravitational interactions. They can become heat and radiation. The tangential components are harder to remove because removing them means removing angular momentum, and angular momentum does not disappear. It can only be transferred. So the first deep answer begins to appear. Everything spins because almost nothing in nature begins with exactly zero angular momentum, and because angular momentum is extraordinarily difficult to get rid of. Even a cloud that is not rotating in a casual description is not truly free of angular momentum. It is a swarm of particles with velocities in many directions, and the statistical sum of those velocities about a center is seldom exactly zero. The universe is vast, and exact cancellations are rare. A tiny imbalance, amplified by collapse, becomes a dominant feature. The rotation that emerges is often not a smooth, solid body spin. It can begin as turbulent swirl, as eddies and streams. Yet as gravity gathers matter, and as collisions damp random motion, the remaining organized angular momentum often expresses itself as rotation around an axis. At the heart of this lies asymmetry. When the laws of physics do not change under rotation, when the outcome of an experiment is the same no matter how the apparatus is oriented in space, there exists, by Noether's theorem, a conserved quantity, angular momentum. Noether's theorem is not an add-on. It is a foundational bridge between symmetry and conservation. If space has no preferred direction, then angular momentum is conserved. The universe, to extraordinary precision, respects isotropy. There is no direction that the fundamental laws favor. Local environments can break symmetry. Magnetic fields can define axes. Mass distributions can define planes. But the underlying laws remain rotationally invariant. And so angular momentum conservation is not merely an empirical fact. It is the consequence of the deep structure of the laws. In daily life, conservation of angular momentum is obscured because torque is everywhere. Feet push on the ground pushes back, friction provides torque. Air pushes on spinning objects, bearings push on axles. The environment is full of opportunities for angular momentum to leak away. But on cosmic scales, the environment is often thin. Space is close to a vacuum. A planet rotates for billions of years because there is nothing substantial to slow it quickly. A star rotates because the internal redistribution of angular momentum may change different layers, but the total remains largely fixed unless winds, magnetic braking, or tides can carry it away. A galaxy rotates because it is an enormous, loosely collisional system where the timescale for dissipating angular momentum through direct friction is effectively infinite. In such systems, angular momentum is not merely conserved. It becomes one of the defining currencies of structure. The simplest mechanical picture of rotation begins with two objects interacting gravitationally. Imagine two masses in space, initially at rest relative to each other, but with a slight sideways velocity component. Gravity pulls them together, but the sideways component causes them to miss a direct collision. Instead, they swing around their common center of mass, tracing curved paths. If nothing removes energy, they can orbit indefinitely. If energy is lost, perhaps through radiation or through interactions with surrounding matter, the orbit shrinks. Yet as it shrinks, the angular momentum remains, so the orbital speed increases. In the most extreme cases, the orbital motion can transform into spin when the objects merge. This is one of the primary cosmic mechanisms for producing rapid rotators, mergers, and accretion. Now widen the picture from two bodies to many. A cloud of gas begins to collapse. As it does, parts of it fall inward. Gas is collisional. It can shock, heat, radiate. Collisions between gas parcels can cancel their radial motions by converting them into heat, which can then radiate away. But those collisions do not cancel angular momentum as easily. When two gas streams collide, their sideways motions can partially cancel if they are opposite, but the total angular momentum about the center must still be conserved. What happens instead is redistribution. Angular momentum is transported outward. Inner regions lose angular momentum to outer regions through torques, viscosity, turbulence, magnetic stresses. This outward transport allows inner material to fall further in, becoming denser, hotter, eventually forming a protostar or a compact object. Meanwhile, the outer material, enriched in angular momentum, forms a rotating disk. A disk is not merely a shape, it is a solution. It is the configuration a collapsing, dissipative system adopts when it can lose energy but must keep angular momentum. A sphere of gas with rotation cannot collapse into a point because that would require infinite rotation speed. Instead, it flattens. Matter falls inward until centrifugal effects balance gravity in the plane perpendicular to the rotation axis, while along the axis matter can still fall. The result is a rotating, flattened structure, an accretion disk, a protoplanetary disk, the disk of a spiral galaxy, the rings of a planet, the disk-like component of many astrophysical systems. Centrifugal force, properly understood, is not a real force in an inertial frame. It is a manifestation of inertia in a rotating frame. But its consequences are real. In the rotating frame, it balances gravity at certain radii, shaping equilibrium. At each radius in a disk, there's a characteristic orbital speed dictated by the gravitational potential. In a Keplerian disk around a central mass, the speed decreases with radius as the inverse square root. In galactic disks, the rotation curve often stays flat over large radii, revealing the influence of dark matter. Yet in every case, the disk is an expression of the same principle. Matter organizes into rotation because it cannot shed angular momentum as easily as it sheds energy. The first time this principle is met, it can feel like a single explanation that covers everything. But the universe is not satisfied with a single layer. The deeper one goes, the more spin splits into multiple related ideas: orbital angular momentum, rotational angular momentum, intrinsic angular momentum in quantum mechanics, vorticity in fluids, circulation in turbulent systems, frame dragging in general relativity, the coupling of spin to magnetic fields, the transfer of angular momentum through gravitational tides, the creation of rotation through instability and asymmetry. Each of these is spin, but each has its own mechanisms, its own mathematical language, its own observational signatures. In classical mechanics, angular momentum is defined as the cross product of position and momentum. L equals R times P. This is not a mere formula. It encodes geometry. Angular momentum is a vector perpendicular to the plane defined by the position vector and the momentum vector. If a particle moves directly toward or away from the origin, r is parallel to p and the cross product is 0, there is no angular momentum. If it moves sideways, r and p are not parallel, and angular momentum exists. The magnitude of L is our p sin theta, where theta is the angle between r and p. This immediately shows why perfect zero angular momentum is rare in nature. It requires sin theta to be exactly 0 for all particles relative to a chosen center, meaning all motion must be purely radial. In any realistic environment, tiny deviations exist. Angular momentum conservation arises because central forces that point along the line connecting bodies, like gravity and electrostatics, exert no torque about the center. Torque is tau equals r times F. If F is parallel to r, then tau is 0. Gravity between 2 point masses is along the line between them. So the torque about the center is 0 and the angular momentum of the two-body system is conserved. This is why orbits are planar and why aerial velocity is constant, as Kepler's second law states. A line from the planet to the sun sweeps out equal areas in equal times. That law is not an empirical curiosity. It is angular momentum conservation expressed geometrically. But the universe is not only made of two-body systems. It is made of many-body systems. And in many-body systems, forces are not always purely central relative to a chosen origin. Mass distributions can be lopsided. Fields can be complex. Bodies can be extended and deformable. In such cases, torques exist and angular momentum can be exchanged between components. Yet, crucially, the total angular momentum of an isolated system remains conserved. The exchange can produce spin in one component at the expense of spin in another. It can align axes, tilt them, precess them, or even reverse rotation in certain layers while preserving the total. This exchange is one of the most important answers to the impression that everything spins. Spin is not only inherited, it is manufactured through interaction. A planet's rotation is not only the residue of the solar nebula's initial swirl. It is also the outcome of impacts, accretion, and tidal evolution. A star's rotation is not only the amplified rotation of its natal cloud. It is also shaped by magnetic braking, by mass loss, by binary interaction, by internal angular momentum transport. A galaxy's rotation is not only a primordial condition. It is torqued by tidal fields from neighboring structures during formation, acquiring angular momentum through gravitational interactions in the expanding universe. To see how gravity can generate spin even if a region starts with no net rotation in a naive sense, consider tidal torque theory in cosmology. In the early universe, a protogalactic region is not perfectly spherical. It is an irregular overdensity. Surrounding mass distributions exert tidal forces, differential gravitational pulls, across the region. These tides apply torques that can spin up the region as it collapses. The angular momentum acquired depends on the misalignment between the inertia tensor of the region, how its mass is distributed, and the tidal shear tensor, how external gravity varies. In an expanding universe with growing structures, such misalignments are natural. The result is that even if the initial velocity field is irrotational in a particular approximation, collapsing regions can acquire angular momentum through these torques before they decouple from expansion and virialize into bound halos. Once a halo forms, its angular momentum is partly in the random motions of particles and partly in coherent rotation. Dark matter halos are largely collisionless. Their rotation is not like a solid disk, but like a net bias in the orbital distribution. Gas, however, is collisional and can cool. As gas falls into the halo, it experiences shocks and radiative cooling, losing energy. It tends to settle into a rotationally supported disk whose angular momentum reflects the halos. Yet, baryonic processes can alter this. Feedback from stars and supernovae can expel gas, preferentially removing low angular momentum material, reshaping the disk. Mergers can add orbital angular momentum, thickening or destroying disks, forming elliptical galaxies whose stars orbit in more random patterns but still carry the angular momentum budget in a different arrangement. The repetition of this theme is not redundancy. It is how the universe enforces its logic. Energy is easy to transform. Angular momentum is not. A collapsing gas cloud can radiate away heat efficiently if it has pathways for radiation, lowering its energy and allowing further collapse. But if it cannot rid itself of angular momentum, it cannot collapse beyond the radius where rotation provides support. So it must find mechanisms to move angular momentum outward. In disks, this is done by viscosity in the broad sense. Any process that transports angular momentum down its gradient. In astrophysical disks, microscopic viscosity is far too small to account for observed accretion rates. The solution is turbulence and instabilities, including the magnetorotational instability, which arises when magnetic fields couple differentially rotating layers, causing an effective outward transport of angular momentum. Magnetic fields act as tension lines. When inner material rotates faster than outer material, magnetic connections can transfer angular momentum outward, allowing inner material to spiral inward. As inner material spirals inward, it releases gravitational potential energy, which can be converted into heat and radiation. Accretion disks around young stars glow in infrared. Around white dwarfs and neutron stars, they glow in X-rays. Around black holes, they can shine with extraordinary luminosity, sometimes outshining entire galaxies as quasars. In every case, the brilliance is powered by angular momentum transport. The disk is a machine that converts the invariance of angular momentum into the possibility of energy release. If the disk persists, it can fragment. In a protoplanetary disk, dust grains collide and stick, building larger aggregates, forming planetesimals, then protoplanets. The angular momentum of the disk is partitioned. Some becomes the orbital angular momentum of planets. Some remains in the star's rotation. Some is carried away by winds and jets. Jets are another expression of spin. Rotating magnetic fields can launch collimated outflows that carry away angular momentum, enabling accretion. The star, forming at the center, would otherwise spin so fast that it would tear itself apart. Yet young stars are observed to rotate more slowly than simple angular momentum conservation during collapse would predict. The missing angular momentum is carried away through a combination of disk locking, magnetic coupling, winds, and jets. In our own solar system, most of the mass is in the sun, but most of the angular momentum is in the planets' orbits, especially Jupiter's. This distribution is not accidental. It is the consequence of how angular momentum is transferred during formation. The sun's rotation is modest because it shed angular momentum. The planet's orbital angular momentum reflects the disks, and their spins reflect both inherited rotation and later impacts. The Earth's spin is not perfectly aligned with its orbital angular momentum. It is tilted, giving rise to seasons. That tilt likely arose from giant impacts during formation, perhaps including the impact thought to have formed the Moon. The Moon itself carries orbital angular momentum, and tidal interactions between Earth and Moon transfer angular momentum from Earth's rotation to the Moon's orbit, causing Earth's day to lengthen and the Moon to recede. Here, on a humanly measurable scale, is angular momentum conservation as a living process. The total remains, but its allocation changes. Tides are an especially intimate mechanism for reshaping spin. A tide is a differential gravitational pull. The near side of one body feels a stronger gravitational attraction than the far side. This difference stretches the body, raising bulges. If the body rotates, the bulges are carried slightly ahead or behind the line connecting the centers, depending on dissipation. That offset creates a torque. Over time, this torque can synchronize rotation with orbit, as in the Moon's synchronous rotation. It can also circularize orbits and align axes. In close binary stars, tidal forces can synchronize spins and orbits and even drive orbital decay. In exoplanet systems, hot Jupiters are often tidally locked, presenting the same face to their star, with permanent day sides and night sides. Tidal torques are one of the few natural processes that can significantly change rotation rates over astronomical times, because they involve real dissipation, internal friction, and because the gravitational coupling can be strong. A planet's rotation can also be altered by atmospheric and oceanic tides, by redistribution of mass through glaciation, by mantle convection. Even Earth's rotation is not constant. It wobbles and varies slightly. But the general persistence of planetary spin arises because space offers little resistance. The spin that exists tends to remain. Now consider stars. A star is a fluid sphere of plasma. It can rotate differentially. The equator may rotate faster than the poles, as in the Sun. This differential rotation is crucial for magnetic field generation through dynamo processes. Rotation and convection twist and stretch magnetic field lines, amplifying them. The resulting magnetic fields can couple to stellar winds, charged particles flowing outward along magnetic field lines. As the wind escapes, it carries away angular momentum. This magnetic braking slows the star's rotation over time. Young stars rotate rapidly. Older stars rotate more slowly. This relationship is so consistent for certain types of stars that rotation can be used as an age indicator, a method called gyrochronology. Yet the story is more complex. Massive stars lose mass through powerful winds and can shed angular momentum quickly. Some stars are in binaries, where mass transfer can spin up a star dramatically, even producing near breakup rotation. When stars die, angular momentum becomes even more dramatic because collapse compresses matter to extraordinary densities. A massive star's core collapses into a neutron star, shrinking from a radius comparable to Earth's to a radius of about 10 kilometers. If angular momentum were strictly conserved in the core, the rotation rate would increase immensely, producing millisecond pulsars. Many pulsars do spin at tens to hundreds of times per second, and some at over 700 times per second. The fastest known neutron stars are astonishing rotors, their surfaces moving at a significant fraction of the speed of light. They are cosmic skaters pulling in their arms to the extreme. Black holes, too, can spin. In general relativity, a rotating black hole is described by the Kerr solution. Its spin affects the structure of space-time around it, dragging inertial frames in a phenomenon called frame dragging. The spin defines an ergosphere where no object can remain stationary relative to distant stars. The spin also affects the innermost stable circular orbit of an accretion disk, influencing how efficiently the black hole can convert infalling mass into radiation. Observations of X-ray spectra and gravitational waves from black hole mergers allow inference of black hole spins. In merging black holes, the orbital angular momentum of the binary and the spins of the individual holes combine to produce the spin of the remnant, with some angular momentum carried away by gravitational waves. Here, in the most violent events in the universe, angular momentum is still conserved, but it can leave the system through space-time ripples themselves. This introduces a crucial refinement. Angular momentum can be carried away by radiation, not only by matter. Photons carry angular momentum, including spin angular momentum associated with polarization and orbital angular momentum associated with wavefront structure. Gravitational waves carry angular momentum as well. Neutrinos can carry angular momentum. In principle, a system can lose angular momentum by emitting radiation anisotropically. But in many astrophysical contexts, the rates and efficiencies are limited. Still, in certain events, like supernovae, where enormous fluxes of neutrinos stream out, angular momentum transport by radiation can be significant in shaping the remnant spin. Now, return again to the most basic question, not as a rhetorical question, but as a demand to keep the reasoning anchored. Why does spin appear so universally? Because the universe begins with motion that is not perfectly symmetric. Because the forces that organize matter, especially gravity, tend to amplify any existing angular momentum during collapse. Because the laws of physics conserve angular momentum due to rotational symmetry of space. Because dissipation removes energy, but tends to preserve angular momentum, forcing matter into rotating configurations like disks. Because interactions and torques redistribute angular momentum, creating spin even where it was not initially organized. Because the environments where cosmic structures form are rarely quiet, they're full of shears, tides, and mergers that supply and rearrange angular momentum. But this answer is still too smooth. It describes the conservation of angular momentum as if it were a single number. Yet in real systems, angular momentum is a field, a distribution, a set of vectors at different radii, in different components, sometimes in different phases of matter. A star has angular momentum in its core and in its envelope, and these can be coupled weakly or strongly depending on internal magnetic fields and waves. A galaxy has angular momentum in its gas, its stars, its dark matter halo, its central black hole. A protoplanetary disk has angular momentum in its gas and dust, in its vortices, in its spiral density waves. The evolution of spin is often the evolution of how angular momentum migrates across these components. Consider a collapsing molecular cloud in a galaxy. Such clouds are cold, dense, and turbulent. Turbulence contains vorticity, local swirling motion. In fluid dynamics, vorticity is the curl of the velocity field. Vorticity can be stretched and amplified, especially in compressible flows. In a collapsing cloud, turbulence can create filamentary structures. Filaments funnel gas into dense cores. The cores can acquire spin from the surrounding turbulent flows. Some of that spin becomes the rotation of the protostar. Some becomes the disk. Observations of star-forming regions show velocity gradients consistent with rotation in cores, but also complex motions that are not simple rotation. The initial conditions are messy. Yet despite the mess, the outcome is often a rotating star with a disk. The universality of the outcome reveals that the conservation and amplification mechanisms are robust to complexity. The disk itself can develop vortices, which are rotating structures within the rotating structure. These vortices can trap dust and aid planet formation. Instabilities can create spiral arms, which transport angular momentum. The disk's evolution is, at its heart, an angular momentum redistribution problem. Matter moves inward, angular momentum moves outward. Planets forming within the disk exchange angular momentum with the disk through resonances, migrating inward or outward. Rings in planetary systems show similar processes. Gravitational interactions with moons create density waves that carry angular momentum, shaping ring structure. The same mathematics, waves, resonances, torque, appears across scales. Now shift to galaxies again, but not in the simplistic image of a smooth, rotating disk. In a galaxy, stars are collisionless on typical timescales. They rarely collide. Gas, however, collides and shocks. The presence of gas allows dissipation, allowing the formation of a thin disk. Stars born from the gas inherit the disk's rotation. But the disk can be heated by perturbations, spiral arms, bars, encounters with satellite galaxies. Bars are rotating structures that can transfer angular momentum between the inner and outer disk and between the disk and halo. They can drive gas inward, fueling central star formation and feeding the central black hole. The evolution of a galaxy's morphology is deeply connected to angular momentum exchange. Even elliptical galaxies, often described as non-rotating, possess angular momentum in the orbits of their stars. Some ellipticals rotate significantly. Others are supported more by velocity dispersion. Their formation history, mergers, accretion, determines the angular momentum distribution. Major mergers can randomize stellar orbits, reducing net rotation, but the total angular momentum remains in the combined system, often appearing in outer stellar halos or in the angular momentum of gas expelled during the merger. The question, does it spin, becomes subtle. Spin is not always visible as a clean rotation curve. Yet angular momentum is always present as part of the dynamical state. Now widen further. Galaxy clusters and a large-scale structure. The universe's matter distribution forms a cosmic web of filaments and nodes. Gas flows along filaments into nodes where clusters form. These flows carry angular momentum. Simulations show that halos acquire spin correlated with their location in the cosmic web, with filaments torquing halos and mergers delivering orbital angular momentum. Clusters may have net rotation, but their dynamics are dominated by random motions and ongoing accretion. Still, angular momentum is present in the orbits of galaxies within clusters and in the intracluster gas. The cluster is not a rigid spinner, but a system whose angular momentum is partitioned among many components. At the largest scales, one can ask whether the universe as a whole rotates. Observations of the cosmic microwave background, the afterglow of the early universe, show extraordinary isotropy, with tiny anisotropies at the level of 1 part in 100,000. A global rotation of the universe would imprint particular patterns. Constraints from observations indicate that if there is any global rotation, it is extremely small. This is a crucial nuance. Everything spins does not necessarily mean the universe as a whole is a rotating rigid body. Instead, it means that within the universe, local and regional structures acquire angular momentum through the processes described. The universe can be globally non-rotating while containing countless rotating subsystems. The conservation laws apply locally and globally, but the net angular momentum of the entire universe may be near zero, with positive and negative contributions canceling on the largest scales. This leads to an even deeper view. Rotation is not something that must be assigned to the universe as a whole. It is a relational property. In Newtonian mechanics, rotation can be described relative to an inertial frame. In general relativity, frames are determined by space-time geometry, and rotation becomes entwined with mass-energy distribution. Yet even there, local measurements of rotation, like the precession of a gyroscope, are meaningful. The gravity probe experiment, for example, measured frame dragging around Earth, confirming that Earth's rotation slightly twists spacetime. In that sense, rotation is not merely motion through space. It is part of how spacetime itself behaves in the presence of spinning mass. But before general relativity is allowed to dominate the narrative, it is necessary to return to something humbler. Why a collapse tends to make a disk rather than a sphere. The reason is not only angular momentum conservation, but also the directionality introduced by rotation. In a rotating cloud, the effective potential includes a centrifugal term that depends on distance from the rotation axis. Along the axis, centrifugal effects vanish. In the equatorial plane, they are maximal. As the cloud collapses, matter can fall more easily along the axis than in the plane, leading to flattening. Collisions among gas particles dissipate energy, allowing them to settle into the plane where their angular momentum vectors align. Over time, the distribution becomes more coherent. The disk becomes thinner as random vertical motions are damped. In collisionless systems like stars and a disk, thickness remains because there is no dissipation, but the disk still forms because the gas that formed the stars was dissipative. The disk is therefore a fossil of dissipation under conservation. It is the signature of a universe where certain quantities are allowed to bleed away and others are not. And this is why spin is everywhere, because gravity makes things fall inward, and when things fall inward with any sideways motion, they must spin faster. The tighter the collapse, the faster the spin. This scaling is not linear. It can be dramatic. For a uniform sphere of mass m and radius are rotating with angular velocity omega, the moment of inertia is proportional to mr superscript 2. If radius shrinks by a factor of 1,000, moment of inertia shrinks by a factor of 1,000,000, and omega increases by a factor of 1,000,000 if angular momentum is conserved. This is why compact objects spin so rapidly. Yet compact objects also show that angular momentum is not perfectly conserved within the collapsing core if there are mechanisms to transport out. In massive stars, internal magnetic fields and waves can transport angular momentum from core to envelope before collapse. During collapse, magnetic torques can redistribute angular momentum. If a collapsing core spins rapidly and has magnetic fields, it can launch jets that carry away angular momentum. The final spin of a neutron star or black hole is therefore a record of complex angular momentum transport. Observations of pulsar spins, black hole spins, and supernova remnants are therefore not merely catalog entries. They're constraints on the physics of angular momentum in extreme conditions. Now, to deepen the story further, the concept of spin must descend beneath the visible rotation of spheres and disks into the more abstract realm of angular momentum in quantum mechanics. In quantum theory, particles possess intrinsic angular momentum called spin. This is not the spin of a tiny ball literally rotating in space. If one tried to model an electron as a classical spinning sphere to reproduce its measured magnetic moment, parts of the sphere would have to move faster than light. The spin is intrinsic, a quantum property that transforms under rotations in a specific way. It is quantized. It comes in discrete units. For electrons, spin is 1/2 in units of the reduced Planck constant. For photons, spin is 1. For many nuclei, spin can be 0, 1/2, 1, 3/2, and so on, depending on how constituent protons and neutrons combine. Quantum spin reveals something profound. Rotation is not only a motion of things in space. It is a symmetry operation acting on the states of systems. In quantum mechanics, a rotation is represented by an operator acting on a state vector in Hilbert space. The conserved quantity associated with rotational symmetry is the angular momentum operator, which includes both orbital and spin components. The quantization of angular momentum arises from the requirement that wave functions be single-valued or transform consistently under rotations, and from the algebra of the rotation group. Spin 1/2 particles transform under the SU2 group, which is a double cover of the ordinary rotation group, so 3. This is why a spin 1/2 particle requires a 720-degree rotation to return to the same quantum state. This is not a metaphor. It has measurable consequences in interference experiments. So even at the deepest level, the universe is built to respect rotational symmetry. Conservation of angular momentum is not a contingent feature. It is embedded in the representation theory of the symmetry groups that define particle behavior. And because angular momentum is conserved, quantum systems organize their energy levels and selection rules around it. Atoms have electron orbitals characterized by angular momentum quantum numbers. The shapes of orbitals, the spectra of light emitted and absorbed, the structure of the periodic table, all bear the imprint of angular momentum. In molecules, rotational states are quantized, producing characteristic microwave spectra. Even in the cold interstellar medium, molecules rotate, and their rotational transitions are observed by radio telescopes, mapping cold gas and galaxies. Rotation, again, is not an aesthetic choice. It is a structural necessity of the laws. But caution is required. Intrinsic spin is not the same as macroscopic rotation, and the documentary must not drift into unrelated territory. The relevance of quantum spin here is that it demonstrates how deeply rotation is interwoven into the symmetry of nature. The same invariance that conserves angular momentum in classical mechanics is present in quantum mechanics, where it becomes operator algebra and quantized values. The universe spins in the sense that the concept of rotation is fundamental to how physical states are defined and conserved. Return again, now, to fluids because much of the visible spinning in the universe is fluid behavior. Gas clouds, stellar interiors, accretion disks, atmospheres. In fluid dynamics, rotation manifests as vorticity. Vorticity can be created by baroclinic effects when pressure gradients and density gradients are not aligned, common in stratified atmospheres and disks. Vorticity can be stretched, leading to stronger rotation in narrower regions, as in tornadoes. In a rotating frame, the Coriolis effect causes moving fluids to curve, organizing flow into rotating systems. On Earth, the Coriolis effect contributes to the spin of large-scale weather systems. In galaxies, rotating disks exhibit shear, and shear can generate and maintain turbulence. In accretion disks, differential rotation is the key ingredient for instabilities that generate turbulence and angular momentum transport. A recurring pattern emerges. Whenever there is differential rotation, different parts rotating at different rates, there is shear. Shear is a source of instability and of energy. It can drive turbulence. Turbulence can transport angular momentum. Angular momentum transport allows accretion and evolution. The disk is therefore not a static spinner. It is a dynamic engine where rotation gradients power internal processes. The same is true in stars. Differential rotation and convection drive dynamos. In planets, differential rotation in atmospheres drives jet streams and storms. In each case, rotation is not merely a motion. It is a reservoir of free energy that can be tapped through instabilities. Yet rotation also imposes order. In rapidly rotating fluids, motions tend to align along the rotation axis, leading to columnar structures known as Taylor columns. Rotation can suppress turbulence in certain directions, leading to anisotropic flow. In planetary atmospheres, rotation contributes to banded structures like those on Jupiter and Saturn. In stars, rotation can affect convection patterns, mixing, and evolution. In galaxies, rotation can stabilize disks against gravitational collapse in certain regimes, described by criteria like the Tumor stability parameter, which balances self-gravity against pressure and shear. Rotation can prevent collapse, but it can also organize collapse into spiral patterns. Again, rotation is both enabling and restraining. Now consider rings and small bodies. Asteroids often rotate, sometimes rapidly. Some are rubble piles held together by gravity and weak cohesion. Their rotation rates are limited by the balance between centrifugal forces and gravitational and cohesive forces. Collisions can spin them up. The YRP effect, torques due to uneven absorption and re-emission of sunlight, can change asteroid spins over time, demonstrating that even radiation can torque a body measurably. Comets spin, often changing as jets of gas erupt from their surfaces, acting like thrusters. These are smaller-scale reminders that spin is easily generated by asymmetry and difficult to eliminate without a sink. At every scale, the mechanisms can be categorized not by a list, but by a repeating logic. Initial conditions rarely have zero angular momentum. Gravity amplifies, dissipation reshapes, interactions redistribute, torques and radiation can modify. The details differ, but the skeleton is the same. And because the skeleton is rooted in symmetry and conservation, it persists across regimes where the matter content, temperature, density, and governing microphysics are vastly different. Even in systems where gravity is not dominant, spin emerges. In electromagnetism, charged particles moving in magnetic fields follow helical paths, effectively rotating around field lines. In plasmas, magnetic fields and currents create rotating structures. In laboratory plasmas and astrophysical plasmas, rotation can arise from instabilities and from imposed fields. But in the universe at large, gravity provides the broad stage, and electromagnetism provides many of the details, especially in how angular momentum is transported and how radiation is emitted. Now the narration returns, again, to the early universe, because the deepest why is not fully satisfied until the origin of angular momentum itself is confronted. If angular momentum is conserved, where does the first angular momentum come from? In an isolated universe, the total angular momentum could be zero. Yet local regions can have non-zero angular momentum because conservation applies to the total, not to each subregion. In the early universe, tiny fluctuations in density and velocity exist. These fluctuations evolve under gravity and pressure. The velocity field in the early universe is often treated as potential flow, irrotational, at linear order. Vorticity decays with expansion in an ideal fluid. So how do bound objects end up rotating? The answer lies in the nonlinearity of structure formation and in the distinction between vorticity and angular momentum. A region can have angular momentum even if the velocity field is initially irrotational, because angular momentum depends on the distribution of mass and velocities relative to a center, and tidal torques can generate it as described. Moreover, vorticity can be generated at shocks, in shell crossing, and through multi-stream flows when matter becomes nonlinear. Dark matter, being collisionless, can develop complex velocity structures. Gas can develop shocks that generate vorticity. In a nonlinear regime, the simple decay of vorticity no longer applies. The cosmic web is a vorticity factory at its intersections and shocks. Thus, even if the early universe begins in a state with little vorticity, the later universe can be full of rotating structures. This is an important deepening. Spin is not necessarily primordial in the sense of an initial cosmic whirl. It is emergent from gravitational instability in an expanding universe with fluctuations. The very act of structure formation produces angular momentum through tidal torques and nonlinear dynamics. Rotation is therefore not an added feature. It is a generic byproduct of clumping. Now, to keep the documentary faithful to its purpose, it must not become a catalog of examples. It must remain a continuous unfolding of the same logic, revisited and deepened. So the narrative returns again to the most elemental mathematical statement: angular momentum conservation. In a closed system, dl/dt equals tau under xt. If external torque is zero, L is constant. The power of this is that it is independent of the messy details. A collapsing cloud can be turbulent, magnetized, radiative, chemically evolving. But unless it can exert torque on something external, its total angular momentum remains. The cloud can exchange angular momentum with its environment through gravitational torques from nearby masses, through magnetic coupling to surrounding plasma, through outflows that carry angular momentum away. Yet if the environment is included as part of a larger system, the total still remains. What changes is not whether angular momentum exists, but where it resides. In practical astrophysics, one often uses dimensionless measures of angular momentum, like the spin parameter of a halo, which compares angular momentum to what would be needed for rotational support. Such parameters are found to have relatively narrow distributions in simulations, suggesting that the acquisition of angular momentum during structure formation follows statistical regularities. This statistical universality is another reason everything spins feels true. The processes that generate angular momentum are not rare. They are generic and repeatable across cosmic history. Yet the direction of spin, clockwise or counterclockwise, does not have a universal preference. In a statistically isotropic universe, there is no global handedness. On large scales, spins should be randomly oriented, with correlations induced by the cosmic web. Observationally, galaxies show a range of spin directions. Local alignments exist, but the universe does not appear to favor one direction overall. This is consistent with the idea that total angular momentum is near zero globally, with local regions acquiring angular momentum through interactions that are equally likely to produce either sense of rotation. The documentary now sinks into a quieter, more methodical pace, as if walking closer to the mechanism rather than being dazzled by the outcomes. Consider a simple collapsing cloud of n particles. Each particle I has mass m_I, position vector r_I, and velocity v_I relative to some origin. The total angular momentum about the origin is L equals sigma m_I r_I times v_I. This sum can be decomposed into the angular momentum of the center of mass motion and the internal angular momentum about the center of mass. The internal angular momentum is what matters for spin. If the center of mass is used as the origin, L represents internal rotation and orbital motions within the system. As the system collapses under gravity, particles accelerate toward the center. Their velocities change. But because the gravitational forces are internal and central between particles, the total internal angular momentum remains constant unless torques from external masses act. What happens to the shape? If the system has no dissipation, it can undergo violent relaxation. a process in which the gravitational potential fluctuates rapidly as the system collapses and rebounds, redistributing energies among particles. The system settles into a quasi-equilibrium where the distribution of orbits supports the mass distribution. Angular momentum is conserved, but can be redistributed among particles. The result can be a triaxial ellipsoid, a rotating bar, or a halo with modest net spin. If the system has dissipation, like gas cooling, it can radiate energy and settle into a flatter configuration. The presence or absence of dissipation determines whether angular momentum leads to a disk or remains as a statistical bias in orbits. This distinction clarifies why dark matter halos are not thin disks. Dark matter does not radiate. It cannot dissipate energy easily. It therefore cannot collapse into a thin disk even though it has angular momentum. Instead, it forms a roughly spherical or triaxial halo, with angular momentum expressed in the distribution of particle orbits. Gas, on the other hand, radiates and collapses further, forming the visible disk. Thus, in galaxies, the very visibility of rotation, spiral arms, disk flattening, is tied to the dissipative nature of baryonic matter. The spin is present in both components, but it manifests differently. Now, beyond classical and quantum, there is the relativistic concept of spin as it appears in spacetime. In general relativity, a rotating mass not only moves through space but drags space and time. This is frame dragging. The mathematics describes how the metric around a rotating body includes off-diagonal terms that represent rotation of inertial frames. In the vicinity of a rotating black hole, this effect is extreme. The dragging can force matter to co-rotate, shaping accretion disks and jets. The spin of a black hole can power jets through mechanisms like the Blandford-Znajek process, where magnetic fields tapping the black hole's rotational energy extract power and launch relativistic jets. These jets can extend thousands or millions of light years, influencing galaxy evolution by heating gas and regulating star formation. In this way, spin at the smallest astrophysical scales, black hole horizons, can influence structures at the largest galactic scales. The universality of spin is not only horizontal across scale, it is vertical across causality. At this point, the narrative has climbed through many layers of the same theme. It can now afford to revisit the initial framing with more precision, without becoming repetitive in a shallow way. The phrase, "everything spins," is not strictly true if interpreted as everything undergoes macroscopic rotation. Many things do not spin in a simple sense. Some elliptical galaxies have little net rotation. Some stars rotate slowly. Some objects are tidally locked. Some systems have angular momentum that is stored primarily in orbital motion rather than rotation. Some particles have zero spin. Yet the deeper statement remains. Angular momentum is pervasive, and rotation and orbital motion are the natural expressions of angular momentum in bound systems. Given any process of structure formation in a universe with rotational symmetry, angular momentum will be present, conserved, redistributed, and often amplified into observable rotation. And so, to continue the exploration without drifting, the narration lingers on amplification, because amplification is the bridge between tiny initial asymmetries and dramatic cosmic rotators. Amplification occurs because angular momentum scales with size. For a given angular momentum, smaller size implies higher rotation rate. This is not merely a proportionality. It is a powerful lever. The universe builds small things out of big things. Clouds become cores, cores become stars, stars become compact remnants. Each step can concentrate angular momentum. But amplification is not always permitted to run unchecked because breakup limits exist. A body rotating too fast will shed mass or deform. Thus, many systems must shed angular momentum during collapse. The methods of shedding, winds, magnetic braking, jets, gravitational waves, mass ejection, are therefore not side stories but central. The universe's ability to make stars and planets depends on its ability to move angular momentum around. A protostar forms from collapsing gas. If angular momentum were perfectly conserved within the collapsing matter, the resulting star would rotate near breakup. Observations show that many young stars rotate much more slowly. This implies that angular momentum is transferred outward. The star disk system acts as a coupled rotator. Magnetic field lines connect the star and the inner disk, exchanging angular momentum. Outflows carry angular momentum away. The disk spreads outward as it transports angular momentum outward, even as mass accretes inward. Planets forming in the disk further redistribute angular momentum through gravitational interactions. The final planetary system is a delicate accounting of angular momentum, with orbital angular momentum dominating. In the case of massive star collapse, angular momentum shedding can determine whether a gamma ray burst occurs. If the collapsing core retains enough angular momentum, it can form an accretion disk around the newly formed black hole, launching relativistic jets. If not, the collapse may produce a different outcome. Thus, spin is not only common, it is decisive. In binary systems, spin-orbit coupling is another decisive realm. Two stars orbiting each other carry immense orbital angular momentum. As they evolve, tides can synchronize their spins, transferring angular momentum between orbit and spin. Mass transfer can spin up one star, creating rapid rotation. When compact objects merge, two neutron stars, two black holes, the orbital angular momentum becomes the spin of the remnant, with some radiated away as gravitational waves. The waveform carries imprints of the spins, allowing measurement. Here, spin is an observable encoded in spacetime vibrations. Now, to keep the tone cinematic and observational, the narration slows again, imagining the universe as a sequence of rotating frames nested within rotating frames, each with its own axis, each axis precessing and wobbling under torques. A planet's axis precesses due to torques from its star and moons, changing climate cycles. A spinning top precesses in a child's hand for the same reason. Torque perpendicular to angular momentum changes the direction of the angular momentum vector without changing its magnitude. In celestial mechanics, this is everywhere. Earth's axis precesses over about 26,000 years. Mars' obliquity varies chaotically over longer times. The spins of asteroids tumble. The axes of stars can be misaligned with their planetary systems. The spins of black holes can be tilted relative to accretion disks, causing lents, thirring precession, and warping disks. The universe is not only spinning, it is constantly negotiating the directions of spins through torque and precession. Precession adds another dimension to why spin persists. Angular momentum vectors resist change. When a torque is applied, the response is often a change in direction rather than a simple speeding up or slowing down. This gyroscopic behavior stabilizes rotating systems. It is why bicycles are stable when moving. In astrophysical contexts, gyroscopic effects can stabilize rotating stars and disks against certain perturbations, while also enabling complex behaviors like warped disks and precessing jets. Again, the same mathematics appears. The deeper one goes, the more one realizes that rotation is not an optional feature that can be added or removed. It is a coordinate in the space of possible states of matter and motion. The universe's initial conditions and laws of motion populate that state space in a way that makes angular momentum abundant. The formation of bound structures then turns that abundance into observable rotation. That is the heart of it. The narration now begins to taper in intensity, not by concluding, but by letting the implications settle like dust in still air. The persistent turning of worlds and stars and galaxies is not a cosmic habit. It is the visible signature of symmetry and constraint. The universe does not need to remember how it started in every detail, because angular momentum acts as a memory that is difficult to erase. Energy can be radiated away, and with it much of the chaotic detail of initial motion. But angular momentum remains, reorganized rather than destroyed. Rotation is therefore a kind of fossil record of formation, a preserved trace of the sideways components of ancient motions, amplified by collapse, sculpted by dissipation, rearranged by interaction, expressed in the graceful inevitability of disks and orbits. And as the mind stays with that thought, the turning becomes quieter, less like a spectacle and more like a condition. A molecule rotating in the cold between stars, a disk rotating around a forming sun, a star rotating beneath its own storms, a galaxy rotating through billions of years of accretion and disturbance, a black hole rotating with space-time itself wound tight around it. Each is different, and yet each is the same in the one way that matters. Each is a system that has found a way to exist in a universe where rotation symmetry implies a conserved quantity, and where gravity and interaction make that quantity visible. The sense of inevitability does not remove wonder, it relocates it. The wonder is not that the universe chose to spin, but that the universe is built so that spinning is what happens when matter is allowed to become what it can be under laws that do not care about direction, under forces that pull inward, under processes that let heat escape, but refuse to let angular momentum simply vanish. Turning is what remains when chaos is permitted to cool. Turning is what emerges when collapse is constrained. Turning is the quiet persistence of motion that has nowhere else to go.